Thanks for the introduction and thanks for the invitation. So I'm sorry that I'm not with you, but I will do my best. I do welcome interruptions and questions, so please do not hesitate to ask me those questions. Please do voice them because I don't see my floating control panels. So the main thing that I would like to do essentially in this talk is to generalize Gaussian process regression from input-output functions to graphs, or more precisely to computational graphs. This generalization is motivated by three observations. First, most problems in computational sciences and engineering can be formulated as that of completing a computational graph in which nodes represent variables and edges represent functions. Some of these functions may be unknown, and by completing the graph, I simply mean approximating or recovering these unknown functions. Now, if you replace these unknown functions by Gaussian processes, then you get a simple method for an interpretable method for completing these graphs. Third, since this completion process can be fully automatized, you can in principle reduce the complexity of solving computational sciences and engineering problems to that of drawing graphs. Now, these three observations lead to a framework which I will now describe and present and then illustrate through examples. Okay. Now, in this framework, we define a computational graph as a graph where nodes represent variables and edges are directed and represent functions. So the graph itself represents functional dependencies between functions and variables. So for instance, the following graph is interpreted as the identity xj being equal to f of xi. And we interpret multiple incoming arrows as a sum. So the following graph is interpreted as xj being equal to f of xi plus g of xk plus h of xl. We use square nodes to represent primary variables and round nodes to represent variables obtained through the aggregation of other variables. So for instance, the following diagram is interpreted as z being equal to the vector obtained by concatenating the variables x and y. And this other diagram is interpreted as the following identities holding true. Now, for this graph, the variables of the graph are the entries of this vector x. So we have 6 variables. And the functions of the graph are the entries of this vector. So we have 4 functions. Now, we say that the vector x is a sample from the graph if those variables, if the variables represented by its entries satisfy the functional dependencies represented by the graph. Now, if we are given n samples from the graph with n equals 3 here, then we can see those samples as the rows of some matrix X. So this matrix X has 3 rows because we have 3 samples, and its number of columns correspond to the number of nodes or variables of the graph. Now, for a given sample S, only a subset of the variables of the graph may be observed or measured. And we indicate which one by using this other matrix M, whose entry Si is equal to 1 if variable I is measured in sample S, and 0 otherwise. Now, using that particular matrix M as an example, The following figure shows the observed variables in sample 1. So we do observe those variables or those entries of the matrix X. Those are the observed variables in sample 2. Those are the corresponding entries of the matrix X. And those are the variables observed in sample 3, and those are the corresponding entries of the matrix X. Now, using Python programming notations, write X of M for the subset of observed entries of the matrix X. And now consider the following problem, which we call a computational graph completion problem. Assume that some of the functions of the graph are unknown. I will use red arrows to represent unknown functions and black arrows to represent known functions. Then, given the data, so given the observed entries of the matrix X, approximate all the unknown functions and recover the unobserved entries of the matrix X. Observe that this problem combines a regression problem, that is approximating the unknown functions of the graph, with the matrix completion problem, that is completing the matrix X. And our solution will be to replace the unknown functions by Gaussian processes and compute their map or empirical bias estimator given the data. Now, to describe this general solution, I will first set notations by considering a simple interpolation problem in which you try to approximate an unknown function f, mapping some variable x to some variable y, given the data f of xi equals to yi for I going from 1 to n. Now, we will represent this data as a dashed arrow between the variable x and the variable y. Now, if you replace that unknown function f by a centered Gaussian process with kernel k, then its map estimator is simply its conditional expectation given the data. So you recover Gaussian process interpolation. Now, this interpolant can also be identified as the minimizer of the following optimal recovery problem, which is a variational problem in which the quantity to be minimized is the RKHS norm of the interpolant, given the interpolation constraints. And this interpolant admits the following representer formula, in which I'm writing kxx for the n by n matrix with the following entries, and k dot x for the n vector for the following entries. Now you have to invert that matrix, and the classical way to avoid issues with its possible singularity or bad condition number or overfitting is to add a nugget or a multiple of the identity matrix to that matrix kxx. And this is equivalent to relaxing the interpolation constraints by adding a Gaussian variable to the output of the function f. So in that relaxed setting, the variable yi is no longer equal to f of xi, but to the sum of f of xi and wi, where wi is the centered Gaussian variable of variance defined by the nugget sigma squared. And if you add those noise variables, then the previous GP interpolant turns into the following GP regressor, and the previous optimal recovery problem turns into the following one, in which you minimize the sum of the square of the RKHS norm of the function f and of the random variables wi, given the interpolation constraints f of x plus w equals y. And if you use the constraint to eliminate the noise variables, then you get the following relax and constrain optimization problem. So you rediscover Tikhonov regularization of kernel ridge regression. Now, we will employ a similar strategy to relax the functional dependencies imposed by computational graphs. What this means in practice is that we let subset of the nodes of the graph represent random variables, and we will draw those nodes in blue. And what we mean by the node I being representing a random variable is that we assume that the corresponding entries of the matrix X to be independent, centered Gaussian random variables, vector fields with covariance matrices or operators indexed by the underlying node. Okay. Now we are ready for the solution of this general computational graph completion problem. The precise description of this solution is technical, but I will illustrate it with several practical examples, and one of them will be solving and learning PDEs. So this solution is to replace unknown functions of the graph by independent GPs and compute their map estimator given the observed entries of the matrix X and given the constraints imposed by the graph. This is equivalent to approximating the matrix X and unknown functions with a minimizer of the following variational problem, in which the quantity to be minimized is the sum of the squares of the RHS norms of the unknown functions and random variables, subject to all the constraints imposed by the graph and the observed entries of the matrix X. The optimization variables here are the unknown functions. This candidates Z for our matrix X, and these variables Y that are defined as the output of all the functions of the graph. Observe that the entries of observe that the variable Z entering in the loss are those associated with nodes representing random variables. The kernels and covariance matrices used to define the loss are assumed to be given a priori, but you could also learn them using empirical bias or some variant of cross-validation. The first constraint is defining the variables Y as the output of the functions of the graph. The second and third constraints are imposing the connectivity or structure of the graph. More precisely, the second constraint imposes for all scroll nodes J of the graph the fact that the variable Zj must be the sum of all the variables Y labeled by arrows ending in the node J. The third constraint imposes for all round nodes J of the graph the fact that the variable Zj is the concatenation of the variable Z labeled by nodes I with an arrow from I to J. And the last constraint is the constraint imposed by the observed data. Now, this is an infinite dimensional optimization problem, but if you minimize the loss with respect to the unknown functions first, then you realize that this is a quadratic optimization problem, and you can identify those unknown functions as a function of the optimization variables Y and Z, which are in turn identified by solving the following reduced optimization problem, which is computationally tractable. Now, all the previous equality constraints can be naturally relaxed through the use of noise variables. And if you use that relaxation, then the previous optimization relaxes to the following form. And this relaxation introduces nuggets in the kernel representative formula, enabling the identification of the unknown functions given the variables Z and Y. Now, you can also complete the graph by computing the empirical bias estimation of the underlying GPs instead of their map estimation. This introduces the following log term in the reduced variational problem. And I refer to the following paper by Dunlop, Helen, and Andrew Stuart for differences between map and empirical bias. But the short story is that map has lower complexity, whereas empirical bias has better consistency. Okay, I know that this part was a bit technical, but now I will show you examples. But before I do so, let me just mention that the proposed framework can naturally be generalized to situations where functions are not just acting on variables, but on linear functionals via duality pairing. And these linear functionals could be masses of Diracs composed with differential operators. So for instance, the following diagram where u is mapping x to u of x and its Laplacian at x should be unpacked as the following one, where x is first mapped to the vector whose entries are Dirac at x and a Dirac at x composed with a Laplacian, and then that vector is mapped via duality pairing to the vector whose entries are u of x and delta of u of x. This generalization is relevant to PDE applications, which I will cover later. Now, as a first example, we are going to turn system identification and digital or surrogate modeling into computational graph completion problems. We will use this nonlinear electric circuit as a simple illustration of this application, but evidently you can make the underlying examples as complex as you want. In particular, it could be a full-blown climate system. So our first application concerns the identification or of digital twin or surrogate model of this nonlinear electric circuit whose RLC components are assumed to be unknown and nonlinear. And by nonlinear, I mean that they depend nonlinearly on the underlying current and voltages. We also assume that all the voltages and all the currents in the circuit to be unknown functions of time. So in particular, we don't know how this circuit is being forced. Now, we run the circuit between time 0 and time 10. And at time ts equals to s over 10 for s going from 0 to 99, we observe or measure a random subset of the values of the variables representing the state of the system. So this figure shows the values of the voltage V1 at times when those values are observed. So we make a total of 7 observations or measurements on V1. Now, given those measurements, consider the problem of approximating all the unknown functions, identifying their RLC parameters as a function of voltages and currents, and identifying all the voltages and currents in the circuit as a function of time. These figures show the values of the measured variables at times when they are measured. Observe that compared to a traditional regression problem, the data is too scarce to recover any of those functions independently from the others. To recover them, we have to exploit non-dependencies between functions and variables. To describe this, write x for the vector whose entries are the variables representing the state of the system. So we have 14 of them, and one of them is time. And observe that these variables are related to each other through non-functional dependencies given by the following equations, which are the Kirchhoff laws for this nonlinear electric circuit. Now, we can represent these functional dependencies between variables as a graph where nodes represent variables and directed edges represent functions, with unknown functions colored in red and non-functions colored in black. And our solution is to replace the unknown functions by GPs and compute their map estimator given the data and the dependencies represented by this graph. And these figures show the true and recovered functions using this approach. So the method works surprisingly well, given that the data was quite scarce. So these figures have to be compared to these ones. Now, I will unpack the completion method, which again is the technical part that can be abstracted away and fully automated. To do so, I will formalize the representation of the data. So remember that we run the circuit between time 0 and time 10, and at times ts equals s over 10 for s going from 0 to 99. We observe a measure or subset of the variables of the graph. Now, if for each one of those samples indexed by S, we write X as V for the value of the variable V in sample S, then X as V can be seen as the entry SV of some matrix X that has 100 rows because we have 100 samples, and 14 columns because we are tracking 14 variables. Now, for each one of those samples, we only observe a subset of the variables, which means that we only observe a subset of the entries of that matrix X. And those entries are colored in white in this figure. So for instance, in sample 5, we observe the variables T, V1, I1, and L1 of I1. In sample 58, we observe T, R of I3, and dV3 over dt. And for sample 70, we observe T, I2, and V3. Okay. Now our solution is to replace unknown functions by GPs and compute their map estimator given the data. To describe this, write F for the vector whose entries are the unknown functions to be identified. Write M for the Boolean matrix whose entry SV is equal to 1 if variable V is measured in a sample S and 0 otherwise. And using Python notations, write X of M for the observed entries of the matrix X. Now, to approximate the unknown functions and complete the matrix X, we minimize the following loss, in which Z is our candidate for the matrix X, and I will now unpack that loss. The square norm of F is the sum of the squares of the RKHS norms of the unknown functions with respect to the following Gaussian kernel. Note that this kernel does not add any prior information on those functions besides regularity. The L1 term in the loss enforces dependencies between unknown functions and variables. So for instance, the term highlighted in green enforces the constraint that the variable representing the value of V1 is obtained by mapping the variable T via the unknown function V1. The L2 term in the loss enforces dependencies between known functions and variables. So for instance, that term highlighted in green enforces the constraint that the variables representing the values of I1, I2, and I3 must be such that I1 plus I3 minus I2 is equal to 0. And the last term in the loss enforces constraints imposed by the data. Note that the terms L1, L2, and L3 are soft constraints which can be turned into hard constraints. Now, to minimize the overall loss, we minimize over unknown functions first. And since the problem is quadratic in these unknown functions, we have formulas representing those minimizers as functions of the unknown variable Z. So for instance, the overall loss is quadratic in the unknown function V1, and minimizing over V1 given the variable Z is equivalent to solving a kernel ridge regression problem, whose minimizer is given by the following formula. And if you do the same for all the unknown functions, then you reduce the previous optimization problem to one that depends only on Z, and that one you can minimize with variance of gradient descent or Gauss-Newton. Okay, now as our second example, we are going to formulate the problem of solving and learning nonlinear PDEs as a computational graph completion problem. This formulation is a reinterpretation of the Gaussian process method introduced in this joint work with Yifan Chen, Bamdan Hosseini, and Andrew Stewart. And the main point that I want to make here is that once you have drawn the graph, the computational graph representing your PDE, your problem is as good as solved in the sense that the completion part could be fully automated. Now, the underlying problem, the underlying method can be applied to arbitrary nonlinear PDEs. But for ease of presentation, I will describe it first for the following nonlinear elliptic PDE, in which f, g, and tau are continuous functions such that this PDE has a unique, strong, or classical solution. The nonlinearity in this PDE is tau, which we assume to be continuous. And as an example, you can take tau of u to be u cubed. Now observe that solving this PDE is equivalent to completing the following computational graph. This graph has only one unknown function, which is the solution of the PDE. Now, since this PDE is well posed, you may think that its solution is not unknown, but from a computation perspective, you can only compute with finite information, which means that you can only compute the values of f and g at a finite number of points. Therefore, from an information-based complexity perspective, U is as good as unknown, and the data is obtained by the computation of the values of f and g at a finite number of collocation points in the interior of the domain and on its boundary. Note that this data also corresponds to the observation of subsets of variables of the graph represented by these dashed arrows. Then the proposed completion approach is to replace the unknown function u of the graph by a centered Gaussian process with kernel k defined on the domain omega, and approximate the solution of the PDE with the map estimator of that Gaussian process, given the identities imposed by the graph at the collocation points. So in that expression, the variables zi1 and zi2 are the values of the intermediate variables of the graph at the collocation points xi. These intermediate variables are unknown, but their nonlinear combination through this known function is known as the value of the right-hand side of the PDE at the collocation point xi. Now, this map estimator can be identified as the minimizer of the following versional problem, where the quantity to be minimized is the RKHS term of the function u defined by the kernel k, and the constraints are requiring u to satisfy the constraints imposed by the graph at the collocation points. Therefore, given a kernel k, the proposed approach can be summarized as approximating the solution u dagger of the PDE with a function un, minimizing the following nonlinear optimal recovery problem, in which the quantity to be minimized is again the RKHS norm of the function u defined by the kernel k, and the constraints are requiring u to satisfy the PDE at a finite number of collocation points xi. Note that the PDE constraints at those collocation points depend on whether they are located in the interior of the domain or on its boundary. Then we have the following theorem. Assume that the kernel K is chosen so that its RKHS space is continuously embedded in the suborder space HS for some S greater than the dimension of the space over 2, plus the order of the PDE, which is 2 here. We need that condition to ensure that the PDE can be defined pointwise for the elements of that RKHS. Assume that the solution of the PDE belongs to that RKHS, and assume that the field distance between collocation points goes to 0 as the number of n of those points goes to infinity. Then as n goes to infinity, the approximation un identified by our method converges to the solution of the PDE, where the convergence holds pointwise and in the suborder space HT for all t smaller than s. So this term is essentially saying that the proposed method is guaranteed to converge as the collocation points become dense in the domain if the kernel K is adapted in the sense that the solution belongs to the RKHS space defined by the kernel K, and that space has enough regularity to be embedded in the suborder space containing functions with continuous second order derivatives for that particular PDE. Now, this theorem generalizes to arbitrary nonlinear PDEs, and its general form is described in the following paper. Now, I will present the proof of this theorem, not only because it is simple, but also because it reveals a fundamental mechanism supporting the application of Kernel methods to PDEs. And this proof also generalizes to arbitrary nonlinear PDEs. So first, observe that since U dagger solves our PDE, and since it belongs to the RKHS space defined by the kernel K, this U dagger satisfies the optimization constraints of our variational problem 2. Now, since UN is a minimizer of our variational problem 2, we deduce that the RKHS norm of UN must be smaller than the RKHS norm of the solution of the PDE. Now, since the RKHS space defined by the kernel K is continuously embedded in the subspace HS, we know that the following functional inequality holds for all functions V. Therefore, we deduce that the HS norm of UN must be bounded uniformly in N by a constant times the RKHS norm of the solution of the PDE. Now, since the subspace HS is compactly embedded in HT for all t smaller than S, we deduce that this sequence UN must converge towards some limit in HT and in C2 along some subsequence. And since UN satisfies the PDE at collocation points, and since the field distance between collocation points goes to 0, we deduce that the limit is the solution of the PDE, therefore it is unique, therefore the whole sequence converges. Now, for the practical implementation of the method, this infinite dimensional variational problem can be reduced to a finite dimensional one by introducing the slack variable z corresponding to the values of u and of its Laplacian at the collocation points, and then minimizing over u before minimizing over z. Note that these slack variables are the intermediate variables appearing in the computational graph. Now, given those variables z, the minimization over u is a linear optimal recovery problem, for which we have the following representative formula, which I will now unpack. So in that formula, z is a vector obtained by concatenating the slack variable z1 and z2 corresponding to the values of u and of its Laplacian at collocation points. To describe the other terms, I will write phi for the vector whose entries phi are delta Dirac functions at the collocation points xi, or delta Dirac functions composed with the Laplacian at the collocation points xi. Kx phi is a vector whose entries are obtained by integrating the kernel K supported at the point x against the functions phi, and k phi is a matrix whose entries are obtained by integrating the kernel K against the functions phi and phi. Note that the entries of the vector kx phi and of the matrix k phi are pointwise evaluations of the kernel K and of its Laplacian. So according to this formula, to identify u, we only need to identify the slack variable z. And these variables are identified by plugging this representative formula into the previous optimization problem, which reduces to the following finite dimensional optimization problem over z. Now, to solve this reduced finite dimensional constraint optimization problem, we use the constraints to eliminate one of the optimization variables, which here is the vector z2, whose entries are the values of the Laplacian of u at the collocation points. And we turn this nonlinearly constrained quadratic optimization problem into an unconstrained non-quadratic optimization problem. Now, to solve this unconstrained optimization problem, we simply use a variant of the Gauss-Newton algorithm. This algorithm is an iterative algorithm obtained by successively linearizing the nonlinearity tau around the previous approximation of the solution and by solving a quadratic optimization problem to get the next approximation of the solution. In practice, this Gauss-Newton algorithm converges in 2 to 7 steps, 2 steps for that particular nonlinear elliptic PDE, which means that the complexity of our nonlinear PDE solvers inherits the complexity of inverting dense kernel matrices. And we are currently adapting the algorithm found in this paper to do so in near linear complexity. This algorithm is based on a combination of low-rank approximation and sparse approximation, which is due to something called a screening effect in Gaussian process regression. Okay, so the following numerical experiments compare the convergence of the finite difference method with the convergence of the proposed method using a Gaussian kernel. So you get convergence to machine precision. Now, as mentioned before, this method and its convergence theorem are generalized to arbitrary nonlinear PDEs. And as an example, these figures illustrate the accuracy of the method for Burger's equation when using the following anisotropic kernel in which the length scale of space has been chosen to be smaller than the length scale of time to capture the underlying shock, right? And the reason why we do that is because if you actually look at the solution in time and space, you realize that although it starts developing a discontinuity in space, it is actually quite smooth in time. These figures and this table show the accuracy of the method for Eichhorn's equation with a Gaussian kernel. And here our Gauss-Newton algorithm converges in 6 steps. And what you see here are the contours of the errors, and those are collocation points. Now, this method can naturally be extended to inverse problems. So in principle, you could also apply it to the type of problems that Omar was considering in this talk. As an example, consider the problem of approximating the unknown solution U and unknown coefficient A of the following PDE, given F and G, and given the values of U at a finite number of measurement points, which are colored in pink or magenta in the following figure. Now, the proposed problem can be formulated as completing the following computational graph, where A and U are the unknown functions of the graph, and the known functions are enforcing the structure of the PDE. So here the data is obtained by the measurement of the value of U at the pink collocation points, and the computation of the right-hand side of the PDE at the blue collocation points, and the boundary value G at the orange collocation points. The GP completion is then equivalent to recovering the solution and the coefficient of the PDE by minimizing the sum of the squares of their RKHS norms with respect to 2 possibly different kernels, subject to the PDE being satisfied at the finite number of collocation points on the boundary and in the interior, and also subject to our measurements of the value of the solution at the data measurement points. And as mentioned before, the practical implementation of this method requires the introduction of the intermediate variables of the graph as slack optimization variables in the variational formulation of the map estimation of U and A. And these figures show the true and recovered solution of the PDE and the true and recovered conductivity coefficient of the PDE. The recovery is not exact because we have only 40 data points. The underlying Gauss-Newton algorithm converges in 5 steps. And note that here we are solving both the forward and inverse problem at the same time. Whereas the classical MCMC approach is to iterate between solving the PDE and solving the inverse problem. Furthermore, again, the complexity of the method inherits that of inverting dense kernel matrices. So if you use something like Mattern kernels, you could make this method of near linear complexity. Okay, so this was an application to solving an example for solving and learning PDEs. Other examples include climate/weather modeling and forecasting, learning stochastic dynamical systems, learning Hamiltonian systems, dimension reduction. The underlying principle behind those applications is always the same: draw the graph, replace unknown functions by GPs, and compute map estimators or empirical bias estimators to complete the graph. For SDs, you actually need to compute the empirical bias estimator rather than the map. Now, since artificial neural networks can be seen as particular instances of computational graphs, you can also use the proposed framework to analyze and generalize them. And I don't have the time to cover the examples since I know that you need to leave the room by 5 o'clock. And I will stop here and I will be happy to take questions.